Okay, let's start the session. I hope my voice is audible and my screen is visible to everyone. right? Okay. So welcome back to the seventh live session of Solar Energy Engineering and Technology. Myself Soumya Tiwari. I am PhD scholar at Department of Sustainable Energy Engineering at IIT Kanpur. And in this session, we'll start the solar thermal part. So the very uh, promising application of this solar thermal part is one of its is a flat plate collector. So the basic of flat plate collector as well as the basic of the heat transfer has been basically told in this whole week 7 content. Um, so as usual, what we can do is uh, if you are from mechanical background, this all might seem very familiar to you, especially the heat transfer part. But if you are not from any other background, so it will be um, so that's why I will just give you a brief introduction from all this lecture content, and then as usual we will solve at last some theoretical as well as numerical problem based on this lecture. Okay. So till now, what we have done is we have studied about solar to electricity generation, right? Through PV collector. Now we are coming to a part where solar energy is utilized to generate heat, and that heat is transferred to a heat transfer fluid that could be like water, air, or ethylene glycol, or maybe depending on what application we are aiming for. Basically, you are utilizing the thermal energy of the incoming solar radiation to basically fulfill your application. Okay, so the classic examples are the air heaters or water heating utilizing the solar thermal energy, right? So the classification of this solar collectors can be done, or whether it is concentrating or non-concentrating type. So concentrating type means the solar radiation are okay. Concentrating type are basically where this incoming solar radiation are being concentrated at some point or maybe at a line focus. So uh, by concentrating, what we are trying to achieve is we are trying to basically we are going to get our solar radiation on a large area. But if you want to enhance the heat obtained, or your required heat transfer, what we can do is we can concentrate that whole incoming solar rays or radiation onto a some point or some line that will be a smaller area, thereby the flux will increase, right? The heat flux will increase. Now, in non-concentrating type, we have this flat plate collector, which could either utilize the fluid or liquid or air. So it could be a liquid flat plate collector or air heater flat plate collector. Now, in concentrating time, depending on whether we are trying to concentrate it on a focus, or we are going for a non-focus type. So in focus type, it could be, as I have said, line focus or point focus. So line focus is basically you're trying to concentrate all the incoming solar radiation on a line, that is your focal line, and in point focus is concentrated on a point. So depending on what application you are required. So say concentrating collector utilizes your mainly direct radiation, because direct radiation have a direction. Diffuse radiation does not have a definite direction, it's coming from all the direction, right? So concentrating collector mainly utilizes the direct radiation, and some part is diffuse component also. So these concentrating collector are used when you are required a very high temperature or a very high thermal energy. And non-concentrating type you utilizes both beam as well as diffuse radiation. Now the flat plate collector, if you remember, it has been explained in some very early previous lectures, where the construction has been explained in detail. So this is your basically your glass cover, or it could be a transparent cover, whatever material it could be. It should be a transparent, so all the incoming, most of the incoming solar radiation passes through this glass cover, fall onto this absorber plate. So the absorber plate is could be a copper plate, or it could be a blackened surface to increase the absorption of incoming solar radiation. And beneath it could be your tube in which your liquid or gas, or whatever fluid is you're flowing, to which heat has to be transferred. Okay, so this is the construction of the flat plate collector. And from side and the back your insulation is provided, so that minimum heat loss should be there, right? So this flat plate collector utilizes both the incident and your beam and diffuse radiation, and it's very simple in construction, very cheap, very simple design. But the problem with this flat plate collector is its efficiency is low, right? Its collection efficiency is low. Now coming to the performance indices, if you want to characterize the performance of a flat plate collector, then some parameters are defined here. So first one is the collector efficiency. Collector efficiency means how much of incident solar flux has been actually utilized. So what is the useful energy to the energy incident to the collector. Concentration ratio is the area of aperture to the area of the receiver. So higher this concentration ratio, greater will be the temperature reached, and greater will be your heat transfer, right? So if you see these values, um, you must be aware of these ranges, that for flat plate collector the concentration ratio is 1, the aperture area as well as the receiver area is same, right? And so the temperature reached here is below 100. If we were talking about line focus, then the concentration ratio can reach up to 100. So temperature is around 150 to 400 degrees Celsius, and for point focus it's a order of like 1000. So 500 to 1000 degrees Celsius can be also basically achieved by this concentrating type of collectors, right? So these high temperature application is basically in some thermochemical process also. So some of the endothermic reaction can be driven by the heat utilized from this incoming solar radiation with the help of these solar collectors. Now the temperature range is basically range of temperature to which heat transfer fluid is heated by the collector. Now this I've already explained. This arrangement might be different, but the basic construction is similar to what I've just explained. And along with that we have a header. Header is basically maintaining your incoming fluid and outgoing fluid, which is the your cold fluid and hot fluid. And uh, and basically distribute the water or fluid in these tubes. Okay, now absorber plate, absorber plate, as the name suggests, it's basically used to enhance the absorption of the incoming solar flux. So we can use the good heat conduction material. Also we can use black cover, like painted cover, so maximum absorption should occur. Now the cover system, mainly toughened glass is used, 4 to 5 thickness. But some for a low cost system you can also use plastic transparent. The main aim is that it should be transparent, right? So the maximum incoming flux should pass through this cover. Now insulation and collector box. So we know the at side we have provide insulation. It could be mineral wool, rock wool, glass wool, and the specification are given here that you can go by yourself. Okay, now uh, the absorber pleats are also defined based on what is the extent of wetted area relative to the absorbing surface area. Wetted area means the area which is has been wetted by the fluid, right? To the absorbing surface area means where the absorption of heat or the incoming flux radiation take place. So it has been classified pin and fin type, rectangular or cylindrical full sandwich, or roll bond or semi sandwich type. So in this pipe and fin type, your wetted area and your liquid capacity is low. In water and sandwich type, this both value is very high, and this semi water sandwich type is a intermediate between these two types. Now this performance analysis of flat plate collector. So basically at a steady state you are doing the energy balance. So whatever you incoming solar radiation falls on your absorber plate area, a part of it is utilized and part of it is lost, right? So basically this energy, based on this basic energy balance equation, this equation can be also derived. So this is a flux incident on the top cover of the collector. Okay, so if you remember, this has been already explained in the previous lecture, right? So this is your beam radiation, this is your diffused, and this is total your global radiation, and this is your factor of reflection, and basically this is diffused, and this is for beam radiation. This value you have already calculated, right? If you remember back in some previous lectures. Now out of this only, when it pass through the basically your toughened glass, the transmittivity and absorptivity factors comes into picture. So that's why we have uh, okay, right, so that's why we have included this transmissivity and absorptivity product for beam as well as diffuse radiation in this equation. Okay, I hope this equations are clear, how this equation comes into picture. Now if you want to know the transmittivity of the cover system, it's basically product of transmittivity due to reflection and refraction, and transmittivity due to absorption. Now how to calculate these two factors is what has been told in upcoming few slides, and you have to know in detail how to calculate this basically transmittivity factor. Okay, so if you want to calculate this transmittivity based on reflection and refraction, it is based on the Snell's law, where if say this is your interface, glass and your air interface, right? So if theta 1 is the angle of incidence and theta 2 is the reflected angle, so the Snell's law is given as, and n1 is n1 and n2 are refractive index of the two medium. The Snell's law is given by n2 by n1 is equal to sin theta by sin theta, sin theta 1 by sin theta 2. This you need to remember. Okay, now reflectivity is related to the angle of incident and reflection by these two equations. So basically what you have to do is you have to remember these equations. Direct numerical will be framed on these equations. So how to basically rho 1 and rho 2 are the two component of reflectivities of two component of the polarization, and based on these two values, this reflectivity is uh, basically calculated. If theta 1 is 0, then the formula that you will use is this equation, and transmittivity due to reflection and refraction is finally given by um, this tau r1 and tau r2. So how to calculate this tau r1 and r2, that basically depend on these two values that we have just calculated. So this is has been basically derived for a single cover. So if I would just okay, if I'll just explain you quickly how this derivation is done. So basically whatever solar flux is basically incident on this surface, a part of is been basically refracted, right? So 1 minus rho 1 is actually refracted, and basically it comes to this point, then part of it is been refracted and part of it is been reflected. So in similar fashion it goes on. So you get this basically equation for a single cover, the tau r1 and tau r2 value, and for basically it's m number of covers. So where m is number of covers, you get these two formula. This you need to remember. Okay, so based on these two formula you can calculate this tau r. Okay, now if you want to calculate the transmittivity based on absorption, it's based on Bogger's law, where basically obtained by assuming that the attenuation due to absorption is proportional to its local intensity. So if you are trying to we are taking a very small uh, basically here a small section, and then we are integrating for this whole length of this your cover. then you will get this value. Okay, so this formula, so this formula you need to remember. Direct question will be framed on this also. Now this was for the normal incidence. Okay, 90 degree, right? If it is an angle theta 1, then the formula, modified formula is this one. So basically, uh, tau alpha transmitted due to absorption, based on absorption, equal to e to power minus k. K is your basically extinction coefficient, depending on what material you are going to use. So, and delta c is basically thickness of your cover. Okay, so instead of delta c is basically your path covered. Okay, so here the path is actual to its thickness also. Here the actual path cover is not this a, so say this b dash. Here it's a b, right? So this will be delta c cos theta 2. So this is the modified equation for incident at a certain angle. This formula you need to remember. Now, okay, so this is one of the numerical that has been explained. So similar question will be also framed. So what has been given is the material of glass cover is given, number of glass cover is given, thickness of the each cover is given, refractive index of glass related to air is also given, and extinction coefficient of glass is given. Now we have to calculate this all parameter, right? Rho 1, rho 2, tau r1, tau r2, and then you have to calculate tau r, tau alpha, all the parameters. So whatever you have just studied, the application is explained in this question. So so what has been given? This is your m value, right? Number of cover is given, and this is your thickness of cover. So this is your delta t, right? And what's the reflective index of glass to the cover? This is value given, refractive index n2 by n1, right? And this value is your extinction coefficient. This is your k value, right? So first, what we can do is, we know the theta 1 angle. Okay, so theta 1 angle, say we are going for this 30 degree. So if we know the Snell's formula, n2 by n1 equal to sine theta 1 by sine theta 2, we know the n2 by n1 value, theta 1 value, we can calculate theta 2. This will come to be 19.20 degree. Okay, now we know theta 1 and theta 2. What we can do is, first we can calculate this rho 1 and rho 2 value for different polarization, right? So after obtaining this 2 value, you can also calculate this tau r1 and tau r2, if you remember. So after calculating these two value, what we can do is, we can put it in this equation, and you can calculate tau r1 and tau r2, and then back you can calculate this tau r factor. So okay, so here m is your number of cover. This is 2. Rho 1 we know, and rho 2 we know, right? Based on theta 1 and theta 2, that we can calculate, and then you can calculate this tau r is the average of these two value. And this is for transmittance based on refraction and reflection, and for transmittivity based on absorption. This formula you have studied, that e to power minus k m delta c by cos theta 2, where delta c you know the thickness, m you know the number of cover, k you know the extension coefficient, theta 2 you have just calculated. You can calculate the tau alpha value, and your transmittivity of the basically glass cover is product of these two value. Okay, so this is how a part of this could be your framed question, or this is all the parts cover in a particular single question. Okay, now transmittivity absorptivity product, basically what this tau alpha that we have just seen in the equation, right? This is tau into alpha, this factor we are talking about. So if you remember, okay, this factor we are talking about, how to calculate this factor. Okay, so similar to what I have just told previously also, What we're trying this what this factor signifies is how much of the incident solar flux is actually absorbed by your absorber plate. Okay, so that is the significance or meaning behind this transmittivity absorptivity product. Okay, so the net fraction that is absorbed after deriving this, basically you will get is this formula: tau alpha upon 1 minus into 1 minus alpha your rho d. Okay, so this is an important formula. Okay, now rho d is basically your diffuse reflectivity, depend on whether you are going for one glass cover system or two glass cover system, and it can be also found by determining this value. uh, so now, performance analysis of flat plate collector. As we have just seen the collector efficiency, right? So instantaneous collection efficiency will be useful heat gain upon the incoming whole radiation on the incident on the collector. So it will be QU useful heat gain upon your incident, your flux into area of the collector, right? So the second important term is the stagnation temperature. What does stagnation temperature means? Say that uh, whatever solar flux is coming onto the collector, none of it is utilized, actually utilized to heat your fluid, right? So what it will do is your collector temperature will rise, right? So what is the maximum collector temperature that can be reached for a particular flat plate collector system? That is your stagnation temperature. Okay, so say if nothing is being utilized, then QU value will be 0, and your condition for stagnation temperature will be whatever is incident is basically your lost, right? This equation. So this stagnation temperature is basically used for comparing different collector design, and also to choose the material depending on what is the maximum temperature that it can be reached. You can actually determine what material should is appropriate for this particular flat plate collector system. Now, now in this lecture mainly heat transfer basic is explained. So um, I hope all are aware about the basics of heat transfer. What I can do is, um, okay, so if someone is not from the mechanical background, for them I could just explain it briefly. So basically in thermodynamics, what we use is what we basically discuss is about the amount of heat transfer. But in heat transfer, what we discuss is about rate of energy transfer. Okay, so you know that heat transfer occur due to the temperature difference, always occur due to the temperature difference only. And uh, um, when the two medium reaches the same temperature, then heat transfer ceases. Okay, so this is the basic understanding of heat transfer. Now you know the mode of heat transfer: conduction, convection, and radiation. Conduction, you know that transfer is between two bodies, or maybe between two part of the same body, due to the molecular motion. It could be due to vibration, like heat transfer, then molecular vibration takes place, and then due to this molecular vibration, heat transfer take place. Okay, now the equation that you need to remember is this equation. Okay, this is equation for heat transfer. So this is given by this Fourier law of heat conduction, where it says that the rate of heat conduction is directly proportional to area and temperature difference, and inversely proportional to this thickness. Okay, in the direction of heat conduction. So this is the formula that you need to remember. Now conduction, this k factor is your heat transfer coefficient. Okay, for conduction, this is a material property. It depends on material, and higher this value, this k value, better will be the heat conduction within that material. Okay, so the better the material, the better is for heat conduction, and lower the value of k, it will be more like a heat insulator. Now this is the curve for all the different materials, and note that this temperature coefficient, thermal conductivity coefficient is uh, dependent on temperature also. So as the temperature changes, these value also will change. Okay. Now thermal diffusivity. The thermal diffusivity basically means that how effectively heat is transferred, um, or what you can see is how fast the heat is transferred through the material, rather than say how effectively heat is. Basically it tells about how far. So when heat is basically transferred to a material, a part of it is stored and a part of it is conducted. So if it's more part of is stored, less part of it is conducted, right? So this thermal diffusivity tells about how fast heat diffuses through a particular material. So it's basically the formula for thermal diffusivity is K by rho Cp, where K is your thermal conductivity, basically value, and rho is your basically density, and Cp your specific heat capacity. Okay. So so basically, the larger the thermal diffusivity, the faster the propagation of heat will be in the medium. Now coming to convection, you know that there is actual fluid movement. So there is a heat transfer between a solid surface and adjacent fluid. It could be a liquid or gas, and that fluid is in motion. Then there is combined effect of conduction and the fluid motion. So if you see, if this is a surface, okay, and a fluid is flowing here. So as the fluid flows on this particular solid surface, a boundary layer is formed on this surface. Okay. So first the heat is transferred from this solid material to this boundary layer. Okay. So this stationary boundary layer through the conduction. Okay. And then advection occur. Okay. So it's combination of convection is combination of these two basically phenomena going here. Okay. So the faster the fluid motion, more will be the greater will be the convection heat transfer. And the this convection also involves the change of phase, because while phase change occurs, the fluid motion occur, right? So if you consider the case of boiling and condensation, there also the phase change occur. Okay. So due to phase change, fluid motion occur, and that type of heat transfer is also comes under the convection only. Now it's of two type, natural and basically your forced convection. Natural convection occur due to the density difference. So and say this wall, this is a wall. Okay. So this wall is at higher temperature than is the air here, right? So due to heat transfer to this air, what happens will this air will heat it, and it's as the air will be heated, its density will decrease, it will rise upward, right? And so and the heavier air will come downward. Okay. So a convection uh, basically heat transfer occur here. This is due to this is natural convection due to the density difference resulting in a mass movement. And if this basically mass motion is influenced by some external factor like pump compressor, then it is a forced convection. Now the equation for that is given by here. Okay. If you will see, it is Newton's law of cooling. So this is Ka delta T, and basically this formula you need to remember, where H is your heat transfer coefficient due to convection, A is your area, okay, through which the heat transfer is occurring, and delta T is the temperature difference between your uh, fluid and your wall or the solid surface. Now note that this H is not the property of the material. Okay. It depends on uh, several factors like the surface geometry, the nature of fluid in motion, the properties of that fluid, the velocity of the fluid. Okay. So now these two are very important formula given for Nusselt number. Okay. For natural and forced convection, this you need to remember. Okay. These two formula very important for convection problem. You need to remember. For forced convection, Nusselt number is basically product of or factor of your Reynolds number and Prandtl number, and for natural convection, this is for Grashof number and Prandtl number, or you can say the Rayleigh number. Okay, and this formula you need to remember. Now, note that this N is based on whether the heating or cooling is taking place. If the fluid is heated, then N is 0.4. If cooled, then it's 0.3. Now, this is the numerical based on what we have just studied. So, what water flows inside a tube of 5 centimeter? So, what we have is, this is your tube of 5 centimeter dia, okay, and 3 meter length at a velocity of your 0.8 meter per second. Determine the heat transfer coefficient and the rate of heat transfer. So what we have been asked is H and Q. Note that here what type of heat transfer will occur, but it's between your wall and your fluid, right? So it's a convection problem. So we are talking about H, heat transfer coefficient due to convection, and rate of heat transfer if the mean water temperature is 50 degrees Celsius and the wall is isothermal at 70 degrees Celsius. So your water is at 50 degrees Celsius and your wall is at 70 degrees Celsius. So what is happening is heat is transferring from wall to this water, right? So it's case of water heating. Now the some values is given here. The K value, the nu value, and your Prandtl number is given at 60 degrees Celsius. Note that whatever value we take is at the average temperature of these two value, the wall and the fluid temperature value. So if you take the average of 70 and 50, it will come to 60. That's why this value are given at this 60 degrees Celsius. Okay. Now you know that this is a problem of forced convection, right? So what we want to calculate is your Reynolds number and your Prandtl number. Prandtl number is already given in the question. What we need to know is your Reynolds number. Reynolds number is basically the formula for Reynolds number is your velocity into your diameter upon nu. This is your kinematic viscosity. Okay. So if we see this value, the Reynolds number value comes to be 83,700. Now we know this equation correlation for the convection heat transfer for forced convection, and this is case of heating the fluid. So N value will be 0.4. So we'll put this value to calculate this Nusselt number, and Nusselt number is basically your SD by K. So how this, what is the significance of this Reynolds number, Nusselt number, Prandtl number, Rayleigh number, Grashof number? That are very important things. I think that are given later in the slide. I will explain just after this numerical. Okay. So basically this Nusselt number that you have calculated from this equation, correlation is basically equal to HD by K, where H is your heat transfer coefficient, and you already know the diameter and your K value. We can calculate the H value. After calculating the H value, you can directly calculate the heat transfer, rate of heat transfer, which will be HA delta T for convection. You know the value of H, you know the value of A, you know the delta T. Delta T is 70 minus 50, that will be 20, and you can calculate the value of Q. Okay, so let's first understand this important okay important dimensional number. Okay, so first is the Reynolds number. What Reynolds number significance is, it tells whether the flow is laminar or whether the flow is turbulent. Okay, so it depends, because as the fluid flows onto a surface, there is transition from laminar to turbulent depending on what is the geometry, surface roughness, flow velocity, surface temperature, and what type of fluid we are taking. So basically Reynolds number tells about whether the flow is laminar or whether the flow is turbulent, depending on what Reynolds number value is between which range and for which type of the system. Okay, so if we basically define it mathematically, Reynolds number is basically ratio of inertia force to viscous force. Okay, so the formula for this you need to remember. So it's velocity into your basically your dimension, and depending on um, basically whether we are talking about which system. If you are talking about the pipe, then this is your diameter, and upon viscous force, so for viscous force you have this kinematic viscosity, and if we want to so this will be now dynamic viscosity, so it not will be nu, it will be mu. Okay, so this is the formula that you need to remember. Now Nusselt number significance is basically it tells about within a given fluid layer. So within this given fluid layer, which heat transfer mode is dominant, whether convection is dominant or convection is dominant. So it's basically heat transfer due to its ratio of heat transfer due to convection conduction upon heat transfer due to convection. So basically this is your Nusselt number. Okay, so if you'll put the formula into the this both basically this equation, you will get Nusselt number is HL by K, where LC is your characteristic length. This formula you need to remember. So greater the Nusselt number, more effective is the convection within the given fluid layer. For okay, so if Nusselt number is 1, then what is it's by pure conduction heat transfer is happening. Now, Prandtl number is basically signifies whether in a given uh, uh, flow, what is your thermal boundary layer to your momentum boundary layer. So, if you might have studied the fluid dynamics where your momentum boundary layer is there, okay, and in heat transfer you read about the thermal boundary layer. So it's basically ratio of these two things. So it's the ratio of molecular diffusivity of momentum to molecular diffusivity of heat. So it tells about how quickly heat transfer occurs as compared to the momentum within a given fluid layer. Okay, within within a given system. So uh, for Prandtl number, for gases say the Prandtl number is 1. So what does it signify? That both momentum and heat dissipation in the fluid occur at the same rate. For liquid metal it's very less, and for oil it's very high, okay, as compared to momentum, the heat diffusion. So this is basically significance of Prandtl number. This is the typical ranges of Prandtl number. The next is the Grashof number. If you remember, Grashof number comes while you are dealing with your natural convection system. So basically, it replaces the Reynolds number in the convection relation for the natural convection, and it's basically it's if you see this Nusselt number is a function of Grashof number and Prandtl number for the free convection, right? And the product of these Grashof and Prandtl number is your Rayleigh number. This is also a very important number that we need to know. So Rayleigh number is basically characterizes the laminar to turbulent transition in free convection system. So if you see, there are some correlation. These are some derived correlation that you need to remember while solving the numerical. What is this Rayleigh number into cos beta value? What is the value of this particular term? So which particular Nusselt number equation you are going to use? So this is given for absorber plate to basically correlation between um, inclined parallel surfaces. This is the heat transfer coefficient between inclined parallel. If you're trying to calculate heat transfer coefficient between inclined parallel surface, you first need to calculate this value Ra, Rayleigh number into cos beta. Beta is your the angle between these two parallel surfaces, and if this value lies between this particular range, then you will use this formula. If it's from 5900 to this particular value, you will use this Nusselt formula, and if it lies between this value, you have to use this Nusselt formula. And you already know Nusselt number is your h into your characteristic length uh, by k, right? So from here you can calculate your heat transfer coefficient. Note that the properties are always evaluated at the arithmetic mean of the surface temperature. Okay. Now this is for another correlation. Uh, so this is all the correlation. Basically, you need to first remember these. these three correlation. Now say this uh, question is there. Okay, calculate the convective heat transfer coefficient between two parallel plate. Okay, so we have these two parallel plate. The plates are separated by 20 mm. This distance is given 20 mm. Okay, and inclination of 40 degrees. So it's basically given inclination from the horizontal. So basically this diagram you can see. So this is your horizontal. So these two parallel plates are there, 20 mm apart at a 40-degree from horizontal. Now the plates are separated 20. The lower and upper plate are 50 and 30 degrees Celsius respectively. So the upper plate is 50 degree and the lower plate is at 30 degrees Celsius. Now we have to calculate the convective heat transfer. Note that all the parameters are always calculated the mean temperature of these two plates temperature, right? So if we calculate the mean temperature, it will be 50 plus 30 by 2, which will be 80 by 2, which will come to be 40 degree. So the mean air temperature at 40 degree is given 40 degree Celsius, right? So in Kelvin it will be 313 Kelvin. So these value you can you have to take always at the mean temperature. Now to calculate the convective heat transfer coefficient, what we need to know is your Rayleigh number. Okay, so Rayleigh number is basically your Grashof number and Prandtl number. Basically, it's factor of these two numbers, and which will come to be, if you multiply it, this is the formula for Rayleigh number. This you need to remember. Okay, where G is your gravity, acceleration due to gravity, beta dash is your temperature coefficient, which will be one by T mean. Okay, so your T mean is 313 Kelvin, and your delta T is the temperature difference. L is your length, right? The distance, and alpha is your heat capacity, right? And nu is your kinematic viscosity. So if we'll put all this value into the equation, we'll see G is your 9.81, uh, beta dash is 1 by 313, uh, delta t is your 50 minus 30, it will comes to 20, and your length is your 20 mm. So in meter it will be 20 into 10 power minus 3 whole cube. Upon your alpha is value is given, and your new value is also given, right? So you can calculate the Rayleigh number. It will come out to be this value. Okay. Now, Rayleigh number into cos beta. Beta is your 40 degree. Your inclination angle is given, right? So you can calculate this value. Note that this value is 9450. Now you will go back and check in which range does this lie. So this will be lying in this range, right? So this Nusselt number formula will be used. So you can put all this value into the equation and equate it by HL by K. You know the L value, you know the K value, you can calculate the H value. So I hope it's clear how to calculate basically heat transfer coefficient for different convection and conduction. Now one part is left is your radiation, right? So unlike conduction and convection, radiation does not need any medium. Okay, so it's the fastest way of the heat transfer, and it is how the solar energy reaches to the earth, that we have already seen. So all the bodies above the absolute zero temperature emit the thermal radiation. It's a volumetric phenomena, and say at a body, if the total incident radiation is q, then part of it is being basically reflected from the surface, part of it been transmitted, right? And part of it's been absorbed within the surface. So if you balance this energy, so this will be your equation. Based on this absorptivity, reflectivity, and transmittivity terms are determined. So depending on which type of system you are talking about, whether you are talking about the opaque system, like all the solid bodies are there, then in opaque medium transmittivity will be 0, right? And then this alpha plus rho will be equal to 1. Now what is the black body? Black body is the ideal body. it has been assumed that whatever incident solar radiation or radiation is falling on that black surface, all is absorbed by this body, and it is the body that emits maximum radiation. Okay, so uh, this emissivity factor is if you're talking about any real body, that are basically classified as the gray bodies. Okay, so it's not ideal body, it's actual body, it's real body, or the gray body. So the actual radiation of the gray body at particular temperature to the radiation of black body at the same temperature, this is your emissivity. Okay, and the Stephen Boseman law basically gives the heat transfer due to radiation, which tells that it's heat transfer. The rate of heat transfer is directly proportional to T to power 4, the absolute temperature to the power 4, and its area. Right. So this is the equation. Now, if you're this is for the black body, right? If you're talking about sigma is your Stephen Boltzmann constant, its value is 5.67 in 10 to power 8, 10 to power minus 8 watt per meter square, Kelvin per 4. And this is for the black body. If you talk about the real body, this emissivity factor will comes into picture. Okay. Now this you need to remember. Okay, so black body radiation represent the maximum amount of radiation that can be emitted from a surface at a specified temperature. Now, if you are talking about now we are talking about a single body till now. If you are talking about heat transfer due to radiation between two bodies, okay. So, say at T1 temperature and T2 temperature, then a view factor comes into picture. View factor basically tells about whatever radiation are being emitted from this body, how much of it actually basically receives at this T2 body, okay, body surface. So for that we have defined a view factor. View factor formula is this. You need to remember this formula. It depends on the emissivity of these two bodies and configuration factor. So configuration factor uh, tells about the fraction of energy that leaves the from body 1 to body 2. Okay, so we have the reciprocity theorem. So what you need to remember is this formula. You need to remember, if you calculate this view factor, then based on this view factor, now the heat transfer between two body rate of heat transfer between two bodies will be given by this equation, which will be now we are just incorporating this view factor into the actual equation that we have studied. So it will be sigma a1. If we're talking heat transfer from 1 to 2, then the area will be corresponding to 1, right? And the view factor will be corresponding to from 1 to 2, and this is this temperature of 1 to power 4 minus temperature of 2 to power 4. Okay, so based on what type of system we have, this basically view factor has been simplified. So if you are talking about two infinite parallel gray plane, okay, so this is infinite parallel gray plane. Okay, so the area will be same. Whatever has been emitted from here will be reached here. So your f from, say, this is 1 and this is 2. Okay, so f12 will be equal to f21. So if we'll put this basically this thing into this equation, the view factor will be simplified to this equation. Now if we are talking about concentric cylinder of or sphere, so what we are talking about, we have concentric, say, cylinder. Okay, so say this body is 1 and this body is 2. So uh, whatever has been emitted from 1 is fully being received by this 2 surface, right? So f1 to 2 will be equal to 1. Now if we put this into the equation will be simplified to this. If you are talking about enclosed body of a very small as compared to the enclosure area, say A2, then A2 will be greater than A1, and this ratio A1 by A2 will be A2 is very greater than A1, so it will be negligible. So when you simplify it, then it will be equal to your emissivity of this smaller body. Okay, so I hope you know how this three formula comes depending on what type of system we are talking about. What you need to remember is this formula and this formula. Okay, Okay, that's all about what has been talked about in the lecture. Now, okay. Now, what we'll do is we'll solve some numerical problem. Okay. So, this is the first question. Uh, as usual, I'll give few minutes uh, to basically answer this question. You can write your answer in the chat box. I'll read this question aloud. So, what has been asked is the ratio of energy actually absorbed and transferred to the heat transfer fluid by the collector, useful energy, to the energy incident on the collector is called. Okay, we've got one answer. So, option B. Okay, I'll just discuss this question. So, we have just studied that the ratio of energy actually absorbed and transferred to the heat transfer fluid by the collector, that is your useful energy, to the energy incident on the collector. So, we are talking about uh, collector efficiency, right? So, what has been actually useful upon the incident energy? So, on particular collector area. So, this is your collector efficiency. So, the correct option is option B. Now, the second question is the absorber plate design where low wetted area and liquid capacity is maintained in order to achieve higher temperature for industrial use is called, which type of absorber plate design is this particular thing. Okay, we got one answer, option D. Okay, if you remember, I've just discussed in this live session also. So this was pin and fin type of absorber plate design where your wetted area was very low and your liquid capacity was also low. So in order to achieve higher temperature for industrial use, so this is pin and fin type. The correct option is pin and fin type. Your rectangular or cylindrical full sandwich was basically for high liquid capacity and high wetted area, and for lower temperature, and your roll bond or semi sandwich type of intermediate between these two. Now, the transmittivity of the cover of the flat plate collector based on reflection and refraction is obtained by which of these law? So Mohan has opted for option A. Okay, so if you will recall, we are talking about transmissivity of a cover of a flat plate collector based on reflection and refraction. Okay, so we are talking about tau r. Okay, so if you'll remember this diagram, so what is this is your incident beam, this is your angle of incidence, and this is your, say, angle of refraction. Okay, this is theta 1 and this is theta 2. So if we're talking about transmittivity of the cover based on reflection and refraction, then we are talking about Snell's law, right? Which is given by n2 by n1 equal to sine theta 1 by sine theta 2. So the third option will be correct. Okay, this is for the option you have opted for. This is for transmittivity based on absorption. Okay, now this is the next question. The next question is the question visible? The next question. Okay, so it might be some lagging due to the network. So is it visible now? Okay, okay, fine. So the next question is, what is the value of convective heat transfer coefficient? The value of convective heat transfer coefficient depend on variable influencing convection, such as which of these factors influence the convective heat transfer? Okay, I've got the answer for it. D, all of the above, which is correct because the convective heat transfer depend on surface geometry also. What is the nature of the fluid motion? What is the bulk fluid velocity? So these all parameters are important that influence the convective heat transfer coefficient. Okay, this H value. Now, the next question is when the fluid is heated under forced convection mode, okay, of heat transfer. The heat transfer coefficient can be calculated using this expression. The expression is already given in the question. Now, what has been asked is what will be the value of this n? Okay, it's not very difficult. Okay, so I got answer. So point 0.4, one answer is point 0.4 and another one is point 0.3. Okay, okay. So if we read this question carefully, what is given, what is described in this question is when the fluid is heated. Okay, so this is the key point that basically you have to focus on. Fluid is heated under forced convection mode of heat transfer, then heat transfer coefficient. You know that if the heat fluid is heated, then the Nusselt, this n value will be and for this Nusselt number correlation will be n will be zero point 0.4. If the fluid has been cooled, so if that type of cooling heat transfer would, had been happening, then this n number would be zero point 0.3. Okay, I hope this is clear. Now, transmivity based on dash is obtained by assuming that the attenuation due to absorption is proportional to the local intensity. What what should be the correct option for this particular statement? So one answer we got is option A. What about others? Okay. So we also got option B. Okay. Okay, if you'll remember, for this question, we have taken very small area. This is your delta T, and this was your intensity I, and this was, say, I plus gt. Okay, so this statement is Hooker's law, which is basically used to uh, basically get the transmittivity based on absorption. Okay, the statement is or the basically the this formula is based on the this statement that the transmittivity based on absorption is obtained by assuming that the attenuation or change due to absorption is proportional to the local intensity. Okay, so if you remember, tau alpha uh, equal to e to power minus k delta t. Okay, this was the equation. So the correct option will be option A. I hope this is clear. Now, this is next numerical problem. The air is flowing between two parallel plates separated by 1 inch, having an inclination of 30 degree with the horizontal. Consider the properties of air at this particular temperature. If the temperature of hot and cold plates are given, and then the convective heat transfer coefficient between the plates will be. I need all of you to solve this question and write your answer in the chat box. Okay, anybody got any answer? If not, you can also write the values you have got for Rayleigh number and Nusselt number while solving this question. Okay, let's solve this problem. So what's given here is air is flowing between two parallel plates separated by 1 inch having inclination of 30 degree with horizontal. So the system we are talking about is similar to this. So here we have two plate. Okay, so plate 1 and plate 2, and these are two parallel plate inclined at angle 30 degree with the horizontal. Now what's given is uh, that if the temperature of hot and cold plate, so say this is the hot plate, T1 temperature is given 338 Kelvin, and the T2 temperature is given 308 Kelvin. The distance between these two plates is also given. This is 1 inch. Okay, and the fluid properties, the fluid here is air, and the property is given at 323 Kelvin. So note that this temperature will be the mean of these two temperatures. So T mean will be T1 plus T2 by 2. Okay, so this will be your 338 plus 308 by 2. So this will be uh, 4, and this will be 6 divided by 2. It will come to be 323 Kelvin, right? So this value are given at the T mean temperature only. These three values. Uh, Now what has been asked in the question is the convective heat transfer coefficient. So H value has been asked. Now for that we know the formula. So this we are talking about the force convection, right? So okay. So first we need to calculate the Grashof number. Sorry, this is okay. The sorry, this is the natural convection thing. Okay, so Grashof number we need to calculate. This is which is basically your um, um, Grashof number will be your basically finally we have to calculate relic number also. So directly let's directly calculate this relic number, which is Grashof number into your your Prandtl number, right? and which will formula is G beta dash. This is the coefficient of thermal expansion, and for gases it this beta dash value is so for gases, so here air is there, so this coefficient of thermal expansion beta dash will be 1 by T mean. Okay, so it will be 1 by your T mean is 323. Okay, now this will be zeta beta dash into your temperature difference into your length cube upon your alpha, and then you will have your kinematic viscosity. So this is formula for Rayleigh number. So if we'll put all the value into the equation, we'll get G will be 9.81, beta dash is 1 upon, so, so that's, so it will be Rayleigh number will be 9.81 into beta dash is 1 by 323 into delta T is basically 338 minus 308. Okay, so this will be your 30 degree, right? And L is basically your distance, so it's given in 1 inch, and you know the conversion, 1 inch equal to 0.0254, this will be meter, right? So this will be 0.0254 cube. Alpha, we know the value of alpha, it's given in the question, 2.591 into 10 to power minus 5, and your viscosity value is 1.79 into 10 to power minus 5. So if we'll solve this, then your Rayleigh number will come to be 32,193. So we don't need just Rayleigh number, what we need is Ra cos theta. Okay, so or cos beta, this is the angle, tilted angle, so it will be 32,193 into cos of that angle of inclination is 30 degree, right? So this value will come to be, I think it will come to 27,879.96. This is the Ra cos beta value, and if we'll look into the range, then the corresponding Nusselt number correlation will be 0.229 into your Ra cos beta to power point, this will be 252. Okay, so when we'll put this, this will be basically equal to your HL by K. Okay, so your Nusselt number, if we'll put all the value into the equation, so this will be 0.229 into your 27879.26 to the power 0.252. H is the unknown that we need to calculate. L is your length, so it's in inch, converted to your meter will be 0.20254, right? And K value is also given in the question, which will be 0.0281. We'll solve this, you will get the value of H, which will come out to be 3.3417 watt per meter square Kelvin. So this is your final answer. So if we'll see this is your final answer. Okay, I hope this question, how to solve this question, is clear. Any doubt in this question? Okay, so this is the next question. A long steel rod of 1 inch diameter is to be heated from 743 to 873 Kelvin. It is placed concentrically in a long cylindrical furnace. Okay, calculator will be there. Yeah, you will get the uh, digital calculator depending on which. So basically, exam center you are on. Okay, so I think your digital calculator will be there in your system, right? So it will be computer based exam. So there will be, you will get digital calculator. You will have in your system. So coming to this question, long steel rod of 1 inch dia is to be heated from this particular temperature to 873 Kelvin. It's placed concentrically in a long cylindrical furnace which has inside diameter of 20 centimeter. Inner surface of the furnace is at temperature this much and emissivity of this much. If the surface of the rod has an emissivity of 0.61, then the average rate of heat absorption during the heating process will be. So I request you all to solve this question, and then we'll discuss how later. I'll give some time, and then we'll solve this question. Okay, anybody got any answers? Okay, have you calculated the view factor? Can you just tell me the view factor value? Okay, let's solve this question. So what's given in the question is we have a long steel rod. Its diameter is 1 inch. It is placed concentrically in a cylindrical furnace. Fine. This diameter is given 20 centimeter. Now the inner surface temperature of the furnace is your 1423 Kelvin, and emissivity is given 0.86. Now the surface of the rod, say 1 is this and 2 is this. Okay, so epsilon 1 is given to be 0.61. Now the temperature of 1 has to be basically heated from 743 Kelvin to 873 Kelvin. Now it's been asked the average rate of heat absorption during the heating process. Okay, so what we first need to calculate is your view factor from 1 to 2. We'll calculate view factor from 1 to 2. We are talking about heating of the rod. Okay, so if you remember for concentric basically cylinders, the formula was 1 upon 1 by epsilon 1 plus a1 by a2 into 1 by epsilon 2 minus 1. Okay, so if we'll put the values, it will be 1 upon epsilon 1 is your 0.61, right? Epsilon 1 is 0.61, a1 by a2. So both are cylindrical, so we can directly write in terms of their diameter. So a1 is your 1 inch. 1 inch is your 0.20254 in meter, and your a2 will be this centimeter. It's given in centimeter, so it will be zero point 0.2, right? So it will be zero point 0.2 in meter. So upon 1 by epsilon 2 is your 0.86 minus 1. So your u factor will, if we'll solve this, the value that I have got is 0.6005. Now you got the v factor, right? So what next we have to look is the rate of heat absorption. So initially the temperature was 743, and the final temperature at the end will be 873. So if we'll calculate the initial rate of heat absorption, we know the formula. The Q initial will be your sigma Stephen Boltzmann constant into your A1 into your U factor into your T1 to the power 4 minus T2 to the power 4, right? So for initial, it will be your Q initial will be your 5.67 into 10 to the power minus 8. This is your sigma value. Your A1 value will be your, the heat transfer is this area, right? So it will be your pi into your diameter, it will be your 0.0254, and so then is your mu factor, right? So it will be 0.6005, and your T1 temperature is now initial temperature, so it will be 743 to power 4 minus your T2 temperature is 1423. Okay, so both are in Kelvin. And similarly, the your final, or you can say at the end, what will be rate of heat absorption? Same formula, just the this temperature will change, right? So it will be 5.67 into 10 to power minus 8 into pi into 0.0254 into 0.6005 into your what is T2, 873, right? To power 4 minus your 1423 to power 4. You can solve this, and the Q average value will be this initial plus final, or at the end by 2. So if we'll solve this, the value that we'll get is 9970.04. Okay, so option C. I hope this is clear. Okay, I hope this question is clear. Now, this is another question. Water flows at a velocity of 3.2 meter per second through a tube of 2-inch diameter and 10-meter length. The mean temperature of water and tube wall are at the isothermal condition, which is given 318 and 348 Kelvin. Properties is given at 333 Kelvin. What is the heat transfer coefficient? You can calculate the heat transfer coefficient, and rate of heat transfer also you can calculate. Okay, do we have any answers? Okay, what we have here is uh, let's solve this problem. So what we have here is a pipe in which water is flowing. Uh, the velocity is given 3.2 meter per second, right? I think the diameter was given 2 inch, so it will be 2 into 0.0254, right? So it will come to be 0.0508, okay, meter, and this length is given 10 meter. Now, what else is given? 2 inch, 10 meter long, 3.2 meter per second, and then 318 and 348 are the temperature of water and tube wall. So temperature of water is 318 and this wall is 348 Kelvin, right? So your T mean temperature will be this 318 plus 348 by 2. This will come to be 6 and this will be 6. This will be your 333 Kelvin. At this temperature, your values are given. K value is 0.66 watt per meter Kelvin, and this value is given 0.478 into 10 to the power minus 6 meter square per second, and the Prandtl number is given to this is 2.98, right? 0.98. Now we have been asked what is heat transfer coefficient and what is rate of heat transfer. These two values. We know that it's case of forced convection, so you have your Reynolds number will be calculated, which will be Vd by u. Okay, you know the velocity, it is 3.2. We know the diameter, it is 0.0508 in meters. To convert inch into meter, and your viscosity is 0.478 into 10 to the power minus 6. This value will be the value that I have got is 3.41401 into 10 to the power 5. This is your Reynolds number. Now this is the case where your wall temperature is higher than your water temperature, fluid temperature. So this is case of uh, heat is transferred from wall to the fluid. It's case of fluid heating, right? So we know the first the correlation for forced convection. For Nusselt number it will be 0.023, Reynolds number to power zero point 0.8 into Nusselt number to power zero point. So it's this is value is n, where n is equal to zero point 0.4 for this is for heating case, right? So we have Nusselt number is equal to 0.023, uh, Reynolds number is 3.401 into 10 to power 5 to power zero point 0.8 into your Nusselt, yeah, okay, so this is your Prandtl number, right? This is your 2.98 to power 4, which will be zero point 0.4. And when we'll solve this, basically this will be equal to h e by k, right? So which is equal to, if we will put the value similarly, this will be 0.0508 upon k value is your 0.66. We will solve this equation, you will get the value of h which will come to be 12313.45 watt per meter square Kelvin. This is the value that I have got. Okay, so 12313 so this is close to this value. Okay, so it depends on what how much decimal point you have taken, and so it's similar to this value, so the option D is correct, right? Now the second part is your heat transfer. So for heat transfer, you know Q equal to H A delta T, right? So you know the value of H, you know the value of A. A is now your pi into D. D is your 0.508 into L. L is your 10, and delta T is basically 348 minus 380, which will be your 30 degree, right? So if we'll calculate this, this will come around 5892443.07. This is what the question. The answer is asked in kilowatt, so it will be equal to 589.24 kilowatt. Okay, so this is the correct option. So I have this question is clear. Any doubt in this question? Okay, I have some more questions, but let's see. So let's see this question, numerical problem. So a flat plate collector is made up of GI absorber plate, GI tube fixed on the underside, and two glass cover. The following data are available. The refractive index of glass relative to air is given, angle of incidence is given, and thickness of each cover is given. The transmittivity equation for two glass cover are given by this equation. The reflectivity of the two component of the polarization that has been asked. So you can try this equation, this question, and meanwhile we don't have time left, so I'll also solve the question with you. Okay, so okay, let's solve this question. So what is the given thing in the question? So what we have is, we have this flat plate collector. Okay, um, so here is your absorber plate. Okay, your tubes are fixed underside, and two glass cover are there. Okay, so this is one glass cover and this is two glass cover. So m value here is 2. Now what else is given in the question? N2 by N1. Refractive index ratio is given 1.526. Angle of incidence is given. So say this theta 1 angle is given. So your theta 1 angle is 29.37 degree. And thickness of the cover. So your T1 say thickness and T2 thickness is 4 millimeter. Now in question it has been asked reflectivity of two component of polarization. So what has been asked is your rho 1 and rho 2, right? So first we know the Snell's law, okay? So which is n2 by n1 equal to sine theta 1 by sine theta 2. If we want to calculate sine theta 2, it will be sine theta 1, which will be sine of theta 1 is your 29.37, and divided by your n2 by n1, so it will be your 1.526. So if we'll solve this, your theta sine theta 2 value will be, it will be 0.3214, and your theta 2 value will be 18.75 degree. Okay, so now we know the theta 2 value. So we know the theta 2 value. Now, now we need to calculate rho 1 and rho 2. We know the formula for rho 1. It is basically sine ratio sine square of theta 2 minus theta 1 upon sine square theta 2 plus theta 1. So if we'll put, it will, theta 2 minus theta 1 will come to be minus, it will be 10.623. Okay, and this will be, if you'll add this to theta 1 theta 2 value, it will be 48.117. So this value will be your I think it will come to be 0.0613. Similarly, you can calculate the second value. This is tan ratio, okay? Tan square theta 2 minus theta 1 upon tan square theta 2 plus theta 1. So if you solve this, you will get the value 0.02829. So now, sorry, we know the rho 1 and rho 2 value. Now we have been asked the uh, reflectivity of two component of polarization. So we can further calculate the tau r1 value. Okay, so it will be 1 minus, the formula was given, rho 1. So it is 1 by rho 1 upon 1 plus 2m, I think it's minus 1 into your rho 1. And similarly tau r2 will be 1 minus rho 2 into 1 plus 2m minus 1 rho 2. You can cross check this value. Okay, the formula same. uh, you can cross check this value whether the value are correct or not, matching with your answer or not. So 1 minus rho 1 is your 0.0613 upon 1 plus 2 into 2 minus 1 into 0.0613, and it will be 1 minus 0.02829 upon 1 plus 2 into 2 minus 1 into 0.02829. So we need to solve this both value, and your tau r will be average of these two values. So it will be tau r1 plus tau r2 divided by 2. Okay, so this will come to be 0.844, so 0.085. Okay, so there might be some calculation mistake, but the formula, we'll see where the calculation mistake is there. Okay, I think this value calculation mistake is there. The formula is same, the method is same. Since we are beyond our time limit for this session. uh, you just need to know how to calculate, basically how to calculate this reflectivity of two component of polarization, which will be tau r1, rho 1 and rho 2, and this the transmittivity of glass cover, which if we calculate based on reflectivity and refractivity, this will be this value. So I will rectify this calculation and then upload it on the portal. But I hope the approach to solve this question is clear. And any doubt in the question? Any part of any question that we have discussed till now? Okay, fine. So we'll end this session right here. I hope this session was useful to you. If you have any doubt, you can ask me in the next session also. And so, thank you all for listening. We'll see you in the next session.